Today we're going to present the material related to lecture number 10 of UMass Dartmouth Bioengineering 411 Bioengineering Labs. So today we're going to talk about how to use chromatography techniques to determine the presence of molecules into a mixture as well as to separate molecules from a mixture. So the idea of chromatography is that we use aqueous solutions as an eluent to basically carry a sample through a column that it's packed with beads. These beads interact with the molecules that are in solution through different sorts of interactions that can, electrochemical, physical, polar. And because different molecules have different interactive properties with the beads or with the stationary phase of the beads, they will be eluted at different times. So the idea is that molecules that interact with the packed beads will be retained in the matrix and show up in the outflow at later time points, while molecules that are not retained by the beads are going to show up in your eluent very soon. It is, of course, very obvious to understand that different molecules will have a different set of optimal beads or with which interact. So choosing the right set, the right material in your column becomes a critical part of your chromatography assay. So we're going to talk about two types of chromatography today. There's preparative chromatography, which is basically used to separate molecules from your eluent so that these molecules can be used for downstream processes, as well as analytical chromatography. The analytical chromatography is used basically exclusively for the separation of components to analyze the mixtures, right? What is these mixtures made of, right? So not necessarily analytical chromatography leads to a downstream use of the molecules. What is very important is that they're not mutually exclusive, right? We can have processes that can allow you to do both. So just to give you a little bit of vocabulary for today's class, so we're going to talk about the chromatograph as the instruments, the apparatus that allows for the separation of compounds via chromatography. The chromatogram is the visual output of chromatography, right? It's basically the type of data that will come up at the end of your assay. An analyte is the substance, or it's a molecule, that we want to separate during chromatography. Then we talk about the mobile phase. The mobile phase is the medium in which your analytes are dissolved, and is the medium that moves along the column, or the medium that's carrying your molecules. And then the stationary phase. The stationary phase is instead the substance that's basically filling the chromatography column, right? It's the substance that it's reacting with your mobile phase and it's subtracting from it, or it's kind of slowing down the elution of your analytes. We define the term retention time and the time it takes for a particular analyte to pass through the system, and the solvent from. When you will see next a very simple and rudimental chromatography experiment is called paper chromatography, and the solvent front is the layer of your solvent, right? Is the top front. That's your solvent or your mobile phase move across the chromatography column. Okay, as I said, a first very simple chromatography assay, just analytical chromatography, just to determine what molecules are present in a certain solution, is called planar chromatography. And the idea is that we use we basically use a paper or a layer of solid particle of your stationary phase. The retention factor, RF, is basically determined as the ratio between how long a given analyte travel compare to the how long the solvent or your mobile phase travel. Okay, and this is very important because it's a way to basically normalize the ability of a certain stationary phase to retain a specific molecule. So as you can see here, these are three different schematic depiction of paper chromatography, and you can see that different analytes have different retention time. And as I said, the ratio, the ratio between how much an analyte travel versus how much the solvent front travel determines basically the affinity of your analyte to your paper chromatography media. Because the analyte it's not usually collected at the end of your assay, paper chromatography is just an analytical assay. Just to give you an example, this is a if we paper chromatography assay in where we use a solvent system which is a 9:1 ratio between ether and acetone, and it's used to separate compounds they make chlorophyll, right? And so going from bottom to top, we see, for example, that these chlorophyll compounds, including lutein, vidaxanthine, and neoxanthine, in the yellow range, have a higher retention time than the two major compounds of chlorophyll, chlorophyll A and chlorophyll B, while the least retention time is obtained by the carotene. Okay, so in another example of planar chromatography, it's a thin layer chromatography. Basically, the two things are interchangeable, same process, same idea, same use of the retention time as a parameter to associate affinity between an analyte and a certain stationary phase. The only difference is that in thin layer chromatography, people use different sorts of compounds. They can go from nitrocellulose to other polymer to as their stationary phase. As I said, like paper chromatography, this is just for analytical purposes. An example of thin layer chromatography, that is widely used. It's basically leveraging separation based on polar properties of your molecule and of your stationary phase. So often people use silica gels as your stationary phase, and if you use silica gel on a stationary phase, a polar analyte, an analyte that it has higher polarity is going to show up having a higher retention time, and so travel less compared to a less polar component. And this is how we can separate among compounds that have different polarities by using a highly polar stationary phase compound. Okay, so we talked about this planar chromatography. There are which relies on basically the mostly on the polar affinity between compounds and the stationary phase. Two very common analytic chromatography tools or processes are the gas that depends on actually the physical state of the mobile phase are the GC or gas chromatography and the LC or HPLC that stands for high performance liquid chromatography. The two words say, the gas chromatography uses a mobile gaseous phase as your element that goes through your column, while the HPLC uses a liquid mobile phase. So in the gas chromatography, the idea is that we vaporize your compounds. So for example, gasoline gets vaporized and then it gets injected into your chromatography machine with a mobile phase, which is composed by an inert gas such as hydrogen 2 or helium. And so as the mixture of gas travels through the inner column or the inner chamber, the different compounds, the different components of the gas are going to be absorbed to the column walls or to the packing material that's inside your GC chamber at different rates. And then there are detectors that determine the amount of this molecule through along your chamber. And though this is just an example in where if we see the resulting chromatogram from a GC analysis where we analyze gasoline, right? We can see that we see a clear difference or clear separation of different gasoline compound molecule that depends on actually the number of hydrocarbon rings from the injector to your output, right? And you can see that higher the number of rings, higher is the more you have the number of rings, more you travel down towards your effluent. Okay, in HPLC, it's the mostly, maybe the most or widely used technique for the chromatographic analysis of liquid media. Again, this is mostly just for analytic purposes. I have the mixtures. I want to determine what compounds are in there, and so the idea is that a pump passes pressurized liquid through a column, which is again filled with a certain stationary phase. And then we use UV detector, right, absorbance type of detectors to determine what compounds are present in there. Okay, if this liquid chromatography and gas chromatography don't rely on chemical charge. If we want to separate ions from solutions based on their chemical on their chemical charge, there's a pretty common use technique is called ion exchange chromatography, whereas the idea is that you pass a liquid or your mobile phase, which is neutrally charged, and it contains your protein of interest through a column which is packed with negatively charged beads. Okay, so the negatively charged molecules will eluate much earlier, so will be contained in early elution volumes because they're not going to be attracted by the negatively charged beads, while the positively or largely positively charged compounds are going to react with your beads and therefore being slowed down, right? And you can see, as we have talked about this through the class, we can use pH or salt concentration to adjust the parameters of your chromatography and basically increase or decrease the elution time or the elution volume of specific molecule, right? Because we know that protein charge strongly depends on the pH and electric current that can be applied to a certain media. So just to give you another example of the same process, they're very schematic. If I have a column whose beads they're here on the walls are positively charged, and I put a mix of amino acids, some positively and some negatively charged, the negatively charged will be bound to the positively charged walls, while the positively charged amino acids are going to flow through. Okay, so today, which is basically the objective of this lab, we're going to talk about, we're going to use size exclusion chromatography, and specifically we're going to use gel filtration chromatography. In gel filtration and size exclusion chromatography, the idea is that we can separate compounds based on their molecular weight, based on molecular size. And the idea is that if we steal a column with the porous beads, right? So we have the beads, and where the voids, we have both voids between beads particle, but also voids within the beads, like inside each of the beads. We expect large molecules, right, to just quickly or more rapidly move through the beads and be eluted earlier, while it's very small molecules, small proteins, to basically enter the holes inside your beads and be retained there, and so being eluted later. So just to give another idea, in principle, right, very small molecules enters many pores in the gels and travel slowly and are eluted later. Medium molecule enters just some pores in the gels and so move at the kind of medium intermediate rate, while large molecules cannot enter the pores in your gel, so they're basically just find their way through the gel beads and get eluted very quickly. So the idea in SEC is that we pass a solvent, right, through your gel beads, and we collect, as you'll do today in lab, we collect volumes of constant volumes and record their time, right? And the idea is that at the beginning we're gonna see just a eluted, just the mobile phase to be collected, and then at a certain point the large molecules are going to appear, followed by the molecules that are more and more retained by your column. And then basically by measuring the absorbance, or by quantifying in each of your sample the amount of each of the column, and we can plot it against the volume of your effluent, right? The amount of how much effluent volume has been collected, and obtain these specific chromatographic curves, like in here. So, the two parameters that are very important to estimate for later determining ability of a certain stationary phase to attract or to interact with a certain analyte are called the void volume and the elution volume. The void volume is basically the volume of the voids, right, which is the volume of the space between packing material inside the column, right? And how do I measure that? The volume is the volume that you would collect before any of the large molecules elute, right? This is how much you feel, how much your column contain of just mobile phase, right, that fills the volume. Then we call the other parameter is called elution volume. Instead, is the volume of your buffer that it's required to pass before I see a certain molecule being eluted, right? Okay, so if we calculate the volume, the elution volume for molecule A and one, and we know the void volume, we can calculate the capacity factor K1, which is the ability of your stationary phase to retain molecule 1 as the difference between VE1 and V0 normalized by V0. And this can also be done for a certain molecule or a certain analyte, number 2, right? And so we can determine if a certain stationary phase is selective or retain a molecule 2 compared to analyte or molecule 1 as the ratio between these two capacity factors. So if your selectivity is much larger than 1, then stationary phase basically binds better to it's a better retainer or better binder to molecule 2, while if delta is much less than 1, it's a better retainer of molecule 1, right? Very simple. Okay, so for today's lab, there's a little bit of equations, a very simple equation that we need to take into account, which are also described in the material in the lab material. Is that if we define the total volume of your column as the sum between the void volume, the volume of the beads, and the volume in the pores inside the beads, right? People have determined that the elution volume of a certain analyte can be computed as the sum between the void volume and the product between the so-called gel partition coefficient and the pore volume, the volume of the pores, right? So this gel partition coefficient is basically a property of your stationary phase, which is defined as the fraction of the internal volume which is available to your solutes, right, to your analyte, right? So it's basically a measure of the affinity between your analyte and your stationary phase. I'm sorry. If, for example, if for a large molecule doesn't interact with your pores, right, your gel partition coefficient is 0, and so you would expect your elution volume to be equal to your pore volume, so to be basically be eluted as soon as you're mobile, as soon as you start collecting as soon as you start collecting, it's gonna be eluted at the same amount as your mobile phase. Instead, for very small molecules that are basically stuck in your pores, right, and the KAV is equal to 1. So basically, your elution volume is just the sum of your volume of pores and your void volume, right? So knowing these two equations and rearranging, kind of knowing this relationship and rearranging your previous equation, we can determine the gel partition coefficients, which is basically a measure of the interaction between your stationary phase and your solute, right, and your analyte, through this volume as the difference between VE minus V0 over VI, right? So we can basically perform an experiment, measure these quantities from your gel filtration analysis and estimate KAV. So this is exactly what we're going to do today. So today we're going to apply gel filtration chromatography. We're going to use this CFADEX Z75 beads as your column material. We're going to use just PBS, saline solutions, as your mobile phase, and we're going to add a mixture of blue dextran, cytochrome C, and potassium chromate, 3 compounds with very different molecular weight and therefore different elution expected different elution times as your material. And we're going to use this to estimate the gel partition coefficient for them. So this is just an example of your inert filtration chromatography beads that you're going to use today. This CFADEX G75. It's a widely used material for gel filtration chromatography in analytical biotechnology. And so just to go through your procedure today, right, we're going to, first of all, because we're going to take absorbance reading, we're going to turn off the spectrophotometer, and then we're going to prepare solution of each individual analyte, blue dextran, cytochrome C, and potassium chromate. As you saw in the previous slide, you're going to have to elute volumes in a certain number of tubes. So we're going to prepare 3 clean test tubes, which are going to be labeled from 1 to 30, right? 1 is the first one where we collect the first amount of volume, and 30 is where we collect the last amount of elution volume, right? Then we're gonna get the CFADEX gel powder, phosphate buffer, and glass fiber, and then use them to carefully assemble your gel column. Now, the details of how to carefully assemble the gel column are all present in the lab manual, so please follow those carefully, because a not properly assembled gel column is going to lead to a wrong experimental procedure. Of course, record the gel bead volume. And now let's move to the chromatographic process. So first you're going to mix the solutions and pour them in the column. Once you have poured all your solution into the column, you need to start your timer, right? As soon as you have poured your solution, you are going to add your mobile phase, and your mobile phase is your phosphate buffer. So the mobile phase, it's going to be added for the entire time of the experiment. So observe the blue dextran, which is the biggest molecule, makes its way through the column, and then as soon as you see blue in your coming out from the eluent, start collecting in your eluent in your test tubes in your test tubes at the volume of 1 to 2 milliliter. Every time you have recorded 1 ml or 2 ml, note the time at which this was recorded and put the tube aside and get a new tube. Do this for about 20 to 45 minutes until no more observable color solution is coming out from your column. Then the TA will tell you, will give you a standard curve for the 3 compounds, and will make you measure the absorbance for all these 30 tubes at 3 different wavelengths corresponding to the 3 compounds. And then finally you need to plot your eluted volumes versus absorbance and use this data to estimate your KAV. So you're going to end up with a table like this one, where you have for your absorbance at 460 for one of the compounds, the absorbance at 530 for one of the compounds, and the absorbance at 630 for another one of the compounds. Each row corresponds to all your test tubes that you have picked up. This is the time at which each test tube was collected and recorded. This is the cumulative volume that has passed through. And what you can see that there are maximum of absorbance per each of these compounds, right? This blue dextran at 630 has a peak in absorbance at about 10 minutes with evolution volume of 4.3, then followed by your cytochrome C, and then followed by your chromate at 460, right? So we can use this. You're gonna basically plot. This is the plot, an example of the plot that you're gonna use those data to perform, right? And then what you're gonna do, this one, because this is your blue dextran, right, which is eluted which has a maximum of absorbance at 10.66 minutes, volume 4.3. We consider this as our no interacting tracers, and so we consider its volume, its solution volume of 4.3 ml, the void volume, so its KAV is going to be 0, right? Then we're going to call the chromate. The chromate is eluted at basically 16 minutes, all the way here, right? We assume that the chromate is basically the other tracer, the one that never gets out, or it's basically stuck into our pores. And so it has a KV equal to 1, so we're going to use it to estimate our VT as 16.1. And so we know instead that the maximum for our cytochrome C happens at about an elution volume of 11 milliliters. So we're going to use these three parameters to find the gel partition coefficient for cytochrome C. And this is the end of the lab. So in summary, we introduced chromatography as a way of separating and analyzing a molecule. It relies on these two important phases, the mobile and the stationary phase. And this lab, we are focusing on gel filtration chromatography and using the resulting data in estimating the gel partition coefficient for a specific molecule, which is cytochrome C. Thank you. Bye.